and then you see a single line which is representing plus and minus imaginary with this real value. So this blue line here is connected to this green line or turquoise line here, but it's rotated 90 degrees. And I tried to make a little paper image, which is not so great, but okay, I have this line and this line coming together, two real eigenvalues, and when they come together you're split into two imaginary components which are following like a parabola down here, and the varying the real value while the imaginary value is growing. That's the best I can say it quickly. Now, examining these eigenvalues at low speed, zero speed, in fact you have this and this symmetric with this and this, and that's the classical solution. Holonomic system, it's a falling 2-degree of freedom system. There's two positive roots for exponentially accelerating as you fall, and two negative roots so that you throw it so it's coming up and coming to rest. So two converging and two diverging modes. Now there's a time reversibility, kind of a deep property of rigid body systems, which says that if you have at one speed an eigenvalue, lambda, for the reverse speed you have the negative of that eigenvalue. It's actually a rather deep property, but you can see it from the equation also. All the terms I had were of even order in lambda and velocity. So the eigenvalue is a split symmetric. And another point I want to make is that with the point symmetry, symmetric about the origin, you see this shape, and you see the same shape reflected down there, or inverted through the origin. And in fact, the whole eigenvalue plot is this thing plus this thing. It's one geometric object placed twice. Okay, so I can't spend the time to go into that and review it, but it's kind of intriguing to me. One geometric object that starts off here and here, and then turns into plus or minus omega going down there. And the same thing there, plus or minus omega going this way. And when you have, what that means is if you have a region, as we do, where all the real values are negative, from the green line to the red line, that means in reverse velocity, everything is the most unstable. Everything is positive. Okay, limiting behavior, zero speed is a holonomic system, potential and kinetic energy, double pendulum, I mentioned that already. And at high speed, which is really where we do the writing, what you should notice is that each of these lines is coming away from the origin, and it's going to be asymptotic to a straight line. So asymptotically, you have something which, as the velocity goes towards infinity, the eigenvalue, both the frequency and the real part, are proportional to velocity, or become approximately proportional to velocity. So what that means, if the eigenvalue is proportional to velocity, the eigenvalue is a settling time, or a growth time, or an oscillation time, that means that if you go twice as fast and it wobbles twice as fast, in space, it's the same path. Twice the frequency at twice the speed means the same path on the ground. So you can switch to a space variable, x equals gt. The derivative in space times velocity equals the derivative on time. And this whole basic equation then doesn't show any velocity except in one term right here. And you can see that when velocity is high, you're going to kind of ignore this. Same as if gravity was low. Gravity and velocity appear together, and low gravity is the same as high velocity. There's an example of this where in numerical simulation, here is the bicycle I showed you before with the speed up to 1,000 meters per second. I mean, it's silly, but just to make the point, you see the straight lines. Here's the same bicycle at 10 meters per second with zero gravity. It's the same equation, the same lines. Okay, now stability. And I apologize for people who know this very well. So it's kind of a mixed talk, I think, where some will not have seen this too much, and others have seen it every day. When you have a coordinate equation, there's an algebra to make on these coefficients E, D, C, D, and A, an algebra of their magnitude to assure that all the roots of the equation are in the left half plane, so the real parts are negative, so they represent a stable eigenvalue. And the normal name for this is the Lewis-Hurwitz criteria. Aaron has found something that's a little nicer called the Leonard-Shepard criteria, the same thing basically. And what you have to have, and glossing over some difficulties, small ones, is that the coefficients all have to be positive, and this algebraic combination of coefficients, which I call RH, also has to be positive. And when we look at this for the bicycle, this is always positive. It's the determinant of the positive definite mass matrix. We never have to consider it unless we have a kind of singular bike with very little, with the mass concentrated in a couple of lines. The B is proportional velocity. If you have one sign that's correct, if it's positive for all speeds. These here have a V squared dependent. And depending on the sign of these things, they may start negative, become positive, start positive, become negative, stay positive, or stay negative. So it's a little more interesting. And then lastly, this combination ends up with a quadratic in V squared times V squared, and depending on these coefficients, it can change sign. Now, if you have stable behavior with all eigenvalues negative real parts, there are only two ways that you can lose stability. And one is that an eigenvalue which is real goes from negative to positive. And in that case, you have a zero. You have a real zero of your equation. And the other way is that a pair of complex eigenvalues can go from negative real parts to positive real parts. So the boundary is when you have a pair of purely imaginary. So that's what these two criteria really are. This one is the condition for a real mineral. This is the condition for an imaginary, a pair of imaginaries at zero. So I'm repeating what I just said. Zero is the solution, or plus or minus I omega is the solution. Now, because it's the easiest and because I've done the most work on it, I'm talking today mostly about E. E equals zero. There's much more to the problem, but that's the one which is easiest and where I have the most progress. E equals zero. E is the determinant of K, and it's something which is varying as speed varies. And it has a very important physical meaning, which is the steady state steering torque. So what do I mean? I mean that when you're going in a steady turn, you have a fixed lean angle, you have a fixed steer angle, and you're holding the handlebars, you need a torque to hold them at that angle. Now, are the handlebars trying to turn back to center, or are the handlebars trying to turn more to the left? That's the sign of the torque. That's the sign of the torque. The situation I mentioned is described by the steady state terms, the Ke matrix, which is composed of a gravity part and a velocity squared. And you say when you're riding in a steady turn, the rolling moment is zero. So you turned it. Maybe that puts the mass of your shopping off to one side. You have to balance it with centrifugal force and so on. So there's a combination of steer angle and lean angle, which is in equilibrium.